So last time we did no free lunch theorem, and the theorem essentially said that there is no universal learner. Okay, so regardless of how much training data we have, we cannot have a universal learning algorithm that will learn all type of tasks. Okay, so and we did a proof of that. I don't know if you have gone through the proof. Again, like we completed the proof last time. So if you have not gone through, you go through again if possible. I would like to move forward, okay, leaving the proof for the moment, and if you have any doubt, then we can do the discuss the proof again. Okay, so right now I would like to move ahead. When we do machine learning, the error can be decomposed into two parts. Okay, there is something called so I can write the error decomposition of for a machine learning problem. I can write the error LDHS as approximation error, which is denoted by epsilon APP, and we have estimation error, which is denoted by epsilon EST. So this error is the error that I make while I choose the hypothesis. So this is the approximation error. So usually I choose some hypothesis. So in this case, let's say A epsilon APP is minimum of LDH, okay, and H in H. So machine learning problem involves two steps, right? First step is to choose the hypothesis class H, and second step is for this hypothesis class, find a optimal function that minimizes the training error. Okay, so these are the two steps in machine learning problem. Choose a hypothesis class, that the functions class that you want to fit in a given data. Once you have chosen that, out of those function classes, you choose the one, choose the H function that gives you the least training error, and that we call it HS. Okay, so error can come from both ways. Okay, the choice of your H, so that's the approximation that you have, because you could have chosen different H also, right? So this itself can lead you to error, and then even if you have chosen H, while solving this optimization problem, you may not have solved it very well. So here also you will make some error. Okay, it may not have been the best one from here. Okay, so optimization problem shows up here once I decide the hypothesis class, but there can be error in both. Okay, so here epsilon approximation means this, the H that I choose from H, which is my hypothesis class. Now how bad it was, like how, so this is LD, right? So this is like the true error I will make with this choice of the H. Okay, so that's the first error that you can make, right? Choosing an H which was not good in general, also during testing, right? LD means that, right? So that's the approximation error that you may have made by choosing such H. Okay, that's one problem. And then second one is when you have chosen some, then how well you have solved this problem, that also matters, right? So I may have solved this with some epsilon accuracy again. So there are two types of error then. So obviously, like epsilon estimate can be estimation error could be like LDHS minus minus this. Okay, so from here itself we can also define. So the any type of error just comes from these two, and this we just use this as a definition. So we can explain these two error in words also. So approximation error so this is the minimum risk achievable by a predictor. Minimum risk achievable by a predictor. Remember, risk means the true error, right? And empirical risk is the training error. Okay, so when I'm saying minimum risk, then I mean this. So this is indeed how we define, right? Epsilon APP is the approximation error. So this is the minimum risk achievable by a predictor in the hypothesis class. This term measures how much risk we have because we restrict ourselves to a specific class. Okay, just write down for the sake of understanding. Okay, so this term measures how much risk we have because we restrict ourselves to capital H, right? Ourselves to a specific class, namely so choosing this specific H is also called inductive bias, right? So earlier in the lectures we also refer to this inductive bias. This is the bias that we have, right? It's a bias that I feel that this class of functions is going to work well for the given problem. Okay, so hence it's also called inductive bias. It is your bias because you could have many class of problems to choose from, but you thought of choosing this H, right? So hence it's called inductive bias. And you have to have this inductive bias in machine learning because there is, in general, you don't know, right? So you have to come up with some class. Anyway, there is no universal learner, right? So because we restrict ourselves to a specific class, namely how much inductive bias we have. Approximation error does not depend on the sample size, okay, because this is minimization over the true error. Okay, so it has nothing to do with the sample size. It's how good your H is. Okay, so the approximation error does not depend on the sample size. And is determined by the hypothesis class chosen, right? And is determined by the hypothesis class. Although these are words, it's good to like just write down, slowly think about these things, right? Because this is true error, right? Yeah, although this guy does depend on sample size, the training error. Enlarging the hypothesis class may decrease the error. Obviously, if I increase, it may happen that I got the ideal one after enlarging this H. So this is obvious fact, right? So enlarging H can decrease, right? Enlarging the hypothesis class H h can decrease the approximation error. That makes sense, right? So in case I did not have the ideal one, maybe after increasing, obviously the error will not increase for sure, it will only decrease if I enlarge h. Now let us look into something called estimation error that we have written here, epsilon est. So this is essentially the difference between the, as we have seen, right, it is LD HS minus epsilon approx, right? So this is how it's defined. So this is the difference between approximation error and the error achieved by the ERM predictor. Okay, so just to copy it again, epsilon est was LDHS minus epsilon approx. This is our ERM predictor. So the error, so this is the difference between the approximation error, which we have defined to be like this, and so this is like yeah, so this it was minimum of LDH, okay, where H came from the capital H, right? So so you see what estimation error means. Estimation error means that this is the best I can do, right, given the hypothesis class. The test error that I have, right, and so the test error that I may have is how far from the error that I get from the LDH. HS is coming from the ERM predictor, okay, which is the training process that we use. So the H that we find from the training process, its effect on the true error, and the H that you could have got the optimal one in your H that you may not have found via training. Okay, these are the ways we are trying to see, right? So this essentially says, this error essentially tells us how bad we were in the training. Okay, because our training did not find a good H for which I could have got LDH. It got HS, which is suboptimal than what I could have got ideally. It could be because the sample was not good, or it could be that the optimization problem, the optimization method I used was not good, but but this is what it says. Okay, so what I got from the training, the H predictor I learned, okay, and what could have been possible ideally, okay, it tries to characterize the difference between them. Okay, so the approximation error, as I said, results because of the empirical risk or the training process. Okay, so if the training process was the ideal one, then given the sample was also ideal one and so on, then we would have made it 0. Okay, so the approximation error or I mean estimation error, right? The estimation error results because we had error in the training process, okay, because of the empirical risk. This is empirical risk, which means training error, right? Because of the empirical risk, that is training error. Is only an estimate of the true risk. True risk is this LDH, right? The test error. So we understand this now. So in this case, estimation error does depend on the training process, meaning also it depends on the sample, because HS depends on the sample. Based on the sample, I am finding the best fit. So this error does depend on depends on the training set size or complexity. So we are now left with so-called bias complexity trade-off. Okay, so we face a trade-off now with the approximation error. It's when you are coming up with the inductive bias, the class of functions that you feel is the good one. So that's the bias that you have, and that's the complexity part. Okay, so how good is your training sample size and so on, that determines this. If sample size is very, very large, then I can find a very good H among that. But then there is also this where I have certain bias. So it is a trade-off. If you can recall the overfitting issue that we had before, if we have the hypothesis class which is very big, there is a danger that it will make big errors here. Okay, so there is a trade-off between estimation error and approximation error. Okay, so we characterize this as bias complexity trade-off. So we face a trade-off called bias complexity trade-off. So if we choose H to be very rich class of functions, then we may do overfitting. So that's the test error will be very high, is too strong. Okay, so in this case, so if we choose H to be very rich class, to be decreases the approximation error, obviously, right? So that we know, but at the same time might increase the estimation error, but at the same time might increase the estimation error. So that's the thing about overfitting, right? That's we have been discussing since the beginning, that there is going to be some kind of trade-off. But if you restrict this guy to be very small class, then your approximation error will be big. If I take H to be very rich class, approximation error decreases, but then it might start overfitting and the estimation error is big. If I make H to be very small, then my approximation error is big because my class of function itself was bad. Even though I may be having less error here, but my approximation error will be big. I mean, why we could be making less error here? Let us say in the very boundary case is h has just one function, right? So if h has just one function, then hs is the same as the same h, okay, and it's perfect, right? So if in a very restrictive case, your estimation error will be very small because you didn't allow any. So you feel that it's about the difference, right? It's not telling that it fits the data well. Okay, it's about the training process, right? So this is the trade-off we have. When I restrict h to be very small, approximation error is going to be big. I'm thinking of some examples for this. Let's see if I can cook up some example here. Okay, let me think of an example, but in the meantime I will kind of put some important notes here. So that's okay. So that h be a very rich class, then approximation decreases, but it might increase the estimation error. And on the other hand, okay, the other part of the trade-off, on the other hand, choosing h to be, what did I write? Choosing h to be very rich class decreases the approximation error, but at the same time might increase the estimation error because of overfitting. Okay, so let me just add this, because it may overfit, right? That we have seen several times in the previous classes, right? Okay, so on the other hand, choosing h to be very small, a very small set, reduces the estimation error. Okay, reduces. So are you convinced with this? Like, reduces the estimation error. Reduces the estimation error, but might increase the approximation error. Or in other words, it may lead to underfitting, right? In other words, may lead to underfitting, right? Meaning it didn't really, I mean, the training error itself was bad because I did not provide enough functions. So even training was bad. Forget about the test. So can we create an example, right, to understand this trade-off, right? These two trade-off, right? Can we create? Let us try, right? I will try to create one on the fly. Let's see if it works out. I mean, my favorite is that line fitting, right? So okay, so let us try to see this, right? So I have this set of data points. Okay, it's a regression problem. So let us try to understand the first part, right? Where h is a rich class, right? So let us say order of h is very, very large. Sometimes in maths we write like this, okay? Very large means greater 1. H is small. So what happens if h is very, very large, meaning I allow all types. So let us restrict h to be even set of polynomials, but which have infinite possibilities anywhere. I can have any degree polynomial allowed, let us say. And then obviously it will overfit, right? We have done this many times, so I should not kind of do too much of that. But Okay, the red ones are our test data, right? This is where you want your algorithm to do well, and these ones are train. So this overfitting we have done like several times, so I'm not worried about this part, but I want to like show you the both part, right? That's why I'm doing this again. Okay, so if H is very rich, right? If H is very rich class, very rich meaning I allow all kind of polynomial, then it overfits, right? So maybe in this, maybe the best one is fifth degree polynomial. Okay, basically it will memorize because I'm providing H to be let's say all class of polynomials. So because it's fifth degree, right, it might do a lot of things like that, bends like that, but it makes sure that it goes through the data point, training data, training approximation error notation is, yeah, I mean it should decrease, right? Okay, so yeah, okay, that's fine. So yeah, okay, so so what was the approximation error, right? Let us write down. Okay, so we kind of understand these things, but it's the notations we have to get used to. Okay, the whole point about this right now is understanding these notations that we wrote and what all this means in practice, right? Okay, so in this case, hypothesis class is very rich class, all kind of functions are allowed. And what does this notation mean, right? This notation means is find H in your H hypothesis class, right? Okay? So let me define H to be set of, like let us say a lot of polynomials. Okay? Set of polynomials of degree less than 100. Okay, that is still a lot, right? Polynomials. It's not saying that it has to be infinite, right? It's saying just large. Okay, so for this problem, it's very large. Okay, polynomials of degree. I mean, if we do it infinite, then pack learning says that it may not work out. Okay, but today we will see something called VC dimension, and that kind of tells you that H can be infinite also. Okay, but yet we can learn. Okay, so there is a generalization of that, but if we stick to this, let us say, even if it's not infinite polynomial of let us say degree 100, right? For this problem, it's huge, right? Looking at the data. Okay, so H being a rich class, approximation error will decrease, right? Why is that? Because H being a rich class means that there will be H in the 100 degree polynomial. So these points are also part of the distribution, but the red one was also part of the distribution. Okay, because the distribution D contains both train and test. Okay, so our distribution D contains both and these guys, right? That's what distribution means, right? Out of this distribution, we saw some because someone gave me a label data of cat, dog, whatever, right? And then some were hidden from us for which we will do the prediction, right? So distribution contains both. So since our hypothesis class is rich, it will fit all of them, including the test also, right? So it may be different from the one we have in the training, right? So maybe red is better to, so it could be some 4th degree, 6th degree, it doesn't matter. Okay, so maybe we have done a lot here during training, right? But it doesn't matter. But what matters is that, oh yeah, it should be possible, right? There is a steep jump here, but okay. So if I do a argmin of this, then I can extract the optimal one, right? So let me call this HD. Okay. The hypothesis class that is optimal on the whole distribution. Argmin means the argument H, okay, for which you have this. So this will be the red one, right? So since I allowed a very large hypothesis class, this error LDH is going to be very small for sure, because it fits not just training data, it fits all the data. Okay, train plus test, all data. D means everything. So we have that. Okay. So this part is the first line we are done, right? The rich class, then it decreases the approximation error. Now let us look at the second part, right? But at the same time might increase the estimation error. So estimation error, why it might increase, right? So let us write down the estimation error, right? The main point is like understanding these notations, right? Because in general we know what is going on, right? Overfitting is going on, right? But let us see this in terms of notations, right? Because when you read papers, they write these in terms of these notations. Okay. Okay, so in notations, how do you make sense of this, right? I claim that it might increase the estimation error. So how do you read this? The whole point of going slow on this part is to understand these things, right? So the statement says it might increase the estimation error, almost zero, let us say. Let us make it simple, it's zero, let's say. And what can happen here? This HS, right? On D, right? So this means white one, exactly, white one, exactly. So this is what it says, right? So HS, which was found on the sample, which are the white data points, which is the white curve. Now that HS, now seen on the whole of the distribution, including the red one, it is making some error, right? Because for this point, after training you learn this curve, right? So you are here, but your actual prediction should have been here. This is the error you made, and you can do it also for here, right? So for this new test point, let us say T1, T2, you learn this one, and the optimal one was this guy. Okay, so this is the error, okay, that you are making. Okay, so we can do this delta 1 is delta 2. So let us say among this, the total, the LDHS, which we can characterize in this case, the error is, I mean, if it was a classification problem, then it was like number of points where they differ and so on. So, but what we are doing is a regression problem. Okay, so I hope you can adapt the loss for the regression. In this regression, it's the difference. When it's classification, then we say number of times it should have been predicted 1, but it was 0. Okay, so we count there, right? But here in regression, we take the difference. Okay, but anyway, it doesn't matter. So here, if you see LDHS, if I take this is delta 1 plus delta 2, and this was almost 0, as you said. Okay, so the error, estimation error, can be high. It's high all because I allowed this guy to be very, very, I mean, allowed a lot of freedom to this guy, right? But you can say that what about the, I mean, in this example, especially I made it for you, right? So this case can happen. That's why we are saying may, right? And for that may, I gave you an example. This is the may case, it can happen. You may say it may not happen. Okay, I agree. It may not happen also, but it may happen specifically with this example, right? That's why we use the word may. Okay, you can say, oh, there are cases where it won't. I agree, it won't. Okay, yeah, there are cases where it may not. Okay. Okay, so let us now look into the other one. Okay, on the other hand case, right? What if we have h to be very small? Okay, so let us see the other case in this small area where h, I'm not sure for h, is just, there is a good notation for that, saying it's very small. Okay, but H hypothesis class is very small now. Okay, so what can happen, right? So we done all this, right? Now let us look into this. Small set reduces the estimation error. So let us try to understand this. Why small set reduces the estimation error? Or we can look at the second part first. H being small increases the approximation error for sure. I mean, already we can see that. So both ways it's true, but let us see which one to start with, right? Yeah, it will increase the approximation error, right? Why is that? Because you did not allow a good set of hypothesis class. So now in this case, let us say the rich one was and the poor one is P. Okay, I just gave a notation now. So in the poor one, we say I only allow up to quadratic, right? So let us say HP polynomials degree less than equal to 2. Okay, so at most quadratic I'm allowing, right? So if I allow only quadratic, then let us first see the approximation error, right? On this data itself. So if I allow only quadratic, then the problem we have is, so quadratic may try to do, okay, it just bends once, right? So the quadratic may do something like that, right? Okay, this is the best possible that it is trying to do on all of the data points. Okay, so I'm saying all red, all the distribution. Okay, distribution here means all. So this is the best you could do, and this is certainly not the best. I mean, this is certainly, this is certainly not good, what I'm trying to say, right? Because I made a lot of error here, I made error here, lot of error, right? So it is happening because H restricted to 2, right? So the quadratic can do at best this. So approximation error may, okay, because if the data was already quadratic, then that's a special case, then it fits directly. But in this case, it may increase the approximation error, especially in this example it does. Okay, so the second part we see, right? So approximation error increases, right? So approximation error, which in this case is this guy, right? Okay, I don't think I have to write too many times. So this increases, okay, because degree allowed was 2 only and it's doing bad. Okay, so approximation error increases. Okay, so we did this part right now. And what might happen with the estimation error, right? It says estimation error may reduce. Like, why is that, right? Estimation error may reduce. Okay, that's this guy, right? So if H is small, why would estimation error reduce, right? Because H is small, the possibilities you are given are, in this case, is a constant function, 1 degree, 2 degree, right? So in this case, of course, samples are also important, right? But let us say this sample itself, right? It is given 3 options: constant, linear, or quadratic during training. During training, it's given these 3 options, and some training data is given as well, which is the white ones. Okay, so what this says is that, based on the training data, there are not enough color. Okay, based on the training data, let us say because of these red guys, maybe the curve was like this, but if I have seen only the white ones, maybe the training, the quadratic that will fit will be like this. So what this says in this case is that since your H is restricted, now the error that you are going to make with this guy, the white one, may be closer to the error that you are making with the yellow one. okay, because you did not allow them to vary too much, because both chose quadratic. So they are, in practice we are saying they may not be going too far. The problem could have been if it was rich, then one guy could do this, another guy could do that, and so on, right? But in this case, the estimation error may decrease. Okay, that's what we are trying to say. Okay, so it's always may, because you can always come up with something and say no, I think it's not true. Okay, but what we are trying to say is that, so what we want to understand from all this is that things can be deceiving when you are learning machine learning. Things can be deceiving in the sense that you choose a small hypothesis class, and then you feel that your test error and train error are very similar. So you will think that I'm learning very well because I'm looking at the test error and my training error is kind of similar. So you may think that, okay, maybe this is the best I can do, right? But the problem was you started with a bad hypothesis class itself, because the test error could have been much smaller, and your objective was to learn a function that does do well on the test data. So what might happen here is that you are making an error, let us say 10.3, and here you are making error 9.8. You are thinking that they are close because this is small, but in practice both are high error, right? Which is not good, which was not good in the first place. Both are high error because the set of hypothesis class was small in the first place. Okay, so this difference may look small and you may feel that you have done well, but this is not. Okay, it's like giving an exam where the questions were kind of, I don't know how to make up this, forget it. So so I think we got the idea here. What is the meaning of bias and complexity? Okay, so this ends chapter 5. Now we go to chapter 6, which is VC dimension. Any questions, any doubt? So I have explained, I have given examples for the may case. Okay, but as I said, it may not also. Okay, but so now we are into the 6th chapter, which is, I guess the name itself is VC dimension. Okay, the VC dimension. So the main thing about VC dimension is infinite size classes can be learnable. Infinite size classes can be. So this is the main thing to note. So what we have done in pack learning is, if it is finite, then it's learnable, but we did not say the other way around, right? It's learnable, then it necessarily has to be finite. Okay, so if finite, then learnable, right? Pack learning, right? Or agnostic pack. But this was not a necessary condition. Okay, this was sufficient, right? So what VC dimension says that it's only sufficient, it's not necessary. There are problems where you may allow your hypothesis class to be infinite, but there is some interesting property that matters more than the size of the hypothesis class. Okay, so this is sufficient, but learnable does not necessarily require hypothesis class to be finite. Okay, so this is sufficient but not necessary. So let us see an example on this, like why, in which case, even though the hypothesis class is infinite, but I can learn. Okay, so let us see an example here. So example 6.1, let H be the set of threshold functions over the real line namely, so let us create some hypothesis class which is threshold functions HA such that A in R, where HA goes from R to 0 1 is a function such that HA of x is 1, x less than A. Whenever x less than A, then it's 1, otherwise it's 0. So here 1, so I'm just defining this notation here itself. XA is 1 if x less than A and 0 otherwise. So in this case, as you can see, H, the hypothesis class, is a infinite class, right? Because A can vary. Okay, here. So A is allowed to be all of R. So these functions are characterized by A. So certainly in your H there are infinitely many HAs, right? So this is H is of infinite size. Clearly H is of infinite size, but we will prove that this is learnable, although it is an infinite hypothesis class. So for this we will use a lemma. So this is lemma 6.1. Let H be a class of thresholds. Let H be a class of as defined earlier, then H is pack learnable using the ERM rule with sample complexity of m h epsilon delta is less than equal to floor of log 2 by delta by epsilon. So this is an example where infinite hypothesis class we will prove is learnable. So what is this problem, right? This problem is about classification on the real line. So you will be given some samples, right? Let us say some samples which are here, some samples which are here, and your job is to find a cutoff where you can say that this side belongs to one class and the red one belongs to the other class. The learning problem here is to find a suitable cutoff. Okay, so since I use red for the training, the test, let me use this only. So let us say circles are the another class. So this is your training data, and your job is to say that, job is to basically say which one is on the which side, right? That's what classification means. Okay, so in this case it's on the real line. So basically you want a cutoff somewhere. So in future the test data could be here. So depending on the coordinate of that, right, someone will give you this, then your threshold function that you learned during training, which is this guy, based on the value of this, it will say, oh, you belong to this class. And it may happen the other way also. Some test can happen somewhere here. So based on the value of this guy, the function that you have learned, the threshold function, will say that, oh, you must be this class because you are taking values on those side of the line. Okay, so this is the problem we have, and the set of classifiers we are allowed could be any of these, right? So that's what HA means, right? HA means like set of all. You have you are allowed to have any of these to figure out, right, which is the good cutoff for you. Looking at the data points, remember that these are told to you that this is x. It is told to you that this is 0, right? These are the label data, right? So it is told to you that these guys are x, and it's told to you that these guys are O. Okay, that's what training means, right? Training data means that I'm told certain images have cat, certain images don't have cat. Okay, so based on these, right, I am looking for a good cutoff, right? That's what this classification problem means. So what should be my good cutoff? In other words, what should be my good A, right, for which for all the x's it will be on this side. So you can define that for all these x's which are less than A, you will say, okay, you guys are 1. So we can say that these guys are 1 class, this guys are 0 class, and all these guys who come here, we say that you guys must be 0 because you exceed my threshold. Okay, so this is the problem we are given. So certainly the choice of functions that you are given, the threshold functions, are infinite. Okay, and what we want to claim is that it is learnable in the sense that it may not overfit. Okay, so this is the problem we have. So we can think of the ideal cutoff, okay, hypothetical cutoff that we don't know in advance, obviously. So we can think of this guy as some hypothetical cutoff on the distribution, okay, D. So let me draw this new one. So let us say this A star is the hypothetical cutoff, which is the optimal cutoff you could have found, okay, which we don't know, okay, but let us assume that there is one. So this A will be the one. So let A star, okay, so here A star is the threshold. Let A star be the threshold such that the hypothesis S star, so I also star on the H, which is my optimal. Obviously A star defines the optimal H also, right, because this is the threshold function, right? So this H star x is 1 whenever x is less than A star. So, and since this is the optimal one, hypothetical one, the LD of H star must be 0, okay, because that should not make any error, because this is the ideal one, right? So this is LD of H star. So we are assuming all this, right? Let us say that there is A star, optimal H star, and for which classifies things perfectly, both for white data points, which is the training, and red data points, which are the test. Now let us take some points which is A0 here and which is A1 here, and let us say that these points are such that so I think we should write it now, so step by step, otherwise it will mix up. So we have chosen A star, and then that gave us the optimal hypothesis H star, and we are further characterizing 2 points on both sides of the A star in such a way that so let A naught less than A star less than A1 be such that the probability that x that I take from this distribution is x being A0 A star is equal to probability x that I take from this distribution is of x being A star A1 is equal to epsilon. So A0 A star is an interval. So this is the left interval. So what we are saying is that this A0 and A1 are such that the probability that I will find a point in A0 and A1 is bounded by epsilon, and similarly for the other half, okay, it's bounded by epsilon. Okay, so let us keep this here. We will use this. Now let us go to the training set. So given a training set S, given a training set S, now let us define B naught to be max of all x such that x with level 1 is in S and B1 is min of all x such that x0 is in S. Okay, let us see what this means. Okay, this here is not interval. Okay, not interval, it can be confusing. This is just a pair, okay, sample level pair. Okay, so what this is trying to say, now you are given the training data. Okay, so I can use this figure now maybe. So this is hypothetical. Okay, A star is lying somewhere ideally here, but what we see is the training data, which are the white points. So what, and these are labeled, right? So what we are trying to do is collect all those x with level 1 and take the maximum of that. Yeah, I hope the thing is ordering is okay. Less than will be 1. Okay, so I am on this side, right? So we are left 1 is 1. Okay, left points are 1. So what this is trying to say is find a B naught. So B naught is the max of x. So max basically maximum of all the training points with level 1. Okay, so this in our case will be this guy. In our case, this is this guy, B naught. This is the maximum of all the x which were labeled 1. So we found the B1, B naught, and then we have similarly B1, the maximum minimum of the all the samples that had level 0. Okay, so we understand this. So now we are in the training data and we only have a view of the training, right? A naught, A star are hypothetical. Okay, okay. So now obviously we are supposed to learn, right? In looking at the training data, we are supposed to learn a hypothesis HS, right? Based on the sample, the white data we have, we are supposed to find HS based on this. So since we have taken B naught to be the max and B1 to be the min, HS must be in between B0 and B1, because if HS is here, it will misclassify. If HS is outside, basically if HS is outside B0 and B1, it will misclassify. So HS must be, because I am allowed to take HS to be anything, right? The hypothesis class is very big, so there must be something that I need somewhere here, so that I correctly classify this guy and this guy. Okay, so hence HS must be in the interval B naught B1. So let BS, okay, this is our cutoff function, right? Okay, so so the cutoff point. Okay, so let BS be a threshold corresponding to ERM hypothesis. ERM hypothesis, you can think of this as the way of finding H, right? Training point, right? Training process. ERM hypothesis, HS. So this HS is the threshold that I found after doing this, looking at the samples, and that corresponds to the BS as a threshold. So HS, which implies that, so as I said, BS must be in B naught B1, right? So implies that BS must be in the interval open interval, right, b0 b1. So now our whole idea is that this HS that we learn must give me less error on the whole data, including the red one, right, on the whole distribution, right, train plus test data whole, right. That's when we will say it learned, right. So a sufficient condition for LDHS being less than equal to epsilon. Now we go to that hypothetical thing, right. We said that A0 probability of that being from A star is epsilon and this distance is kind of epsilon. Then we want to characterize, because this is our BS that we found, right. So essentially if this BS somehow appears in here, then from A star it's like within epsilon, right. That's the whole point, right. Our optimal A star is here and A naught is epsilon distance, A1 is epsilon distance, and BS that we learned, if it has to do well on the test data, if it is somehow comes up here, then it will ensure that it's not very far from A star, okay. And then the error which is done on the D, right. So this is the D part, right. This is A star on the D. So if somehow our BS was not so far from A star or within this epsilon or within this epsilon, then I will do well in the in the test error, okay. So a sufficient condition for LDHS less than equal to epsilon is that, so this is a sufficient condition, okay. So is that both B naught is greater than equal to A naught, 1 second, B naught, okay. Yeah, actually we have to look at the B naught also, right. So B naught is our boundary that we got in the training, right, and BS is somewhere lying between B naught and B1, okay. Ideal case is like even B naught is greater than equal to A naught, right. Yeah, I mean that's the best case, right. If B naught somehow gets pushed in here and B1 gets pushed in here, then certainly BS was within that, right. So that's a sufficient case is that, right. A sufficient condition for LDHS being less than equal to epsilon. So BS is somewhere here, B naught is somewhere here, B1 is here. So if these guys were such that B naught somehow lies here, B1 lies here, BS lies somewhere here, then these guys are like quite nice, I mean within epsilon distance, right. So a sufficient condition for the test error to be less than equal to epsilon is that both B naught is greater than equal to A naught and B1 is less than equal to A1, right, and B1 is less than equal to A1. We can take a negation of this also. We can take a negation of this, but I am thinking of a good way to what I can do is that I will write this line and see if it makes sense to you. If not, then I will do one step where I will do the negation. It's like if P then Q. So if this happens, then this happens. So what is the negation of that, right? P implies Q, then contrapositive, not Q implies not P. Okay, so this is the equivalent statement as not Q. So this is like proof technique, right? Not Q implies not P. So here we are saying that if both B naught A naught, B naught greater than equal to A naught, B1 less than equal to A1 implies LDHS less than equal to epsilon. So this is our P and this is our Q, right? Okay. So P is like so what is the statement? P is our B naught. P is our statement that B naught greater than equal to A naught and B1 less than equal to A1, and Q is our statement that LDHS is less than equal to epsilon, and what we have is P implies Q. So in other words, we can say that not Q implies not P. So not Q is the statement that LDHS is greater than epsilon, and not P is the statement that B naught less than A naught, and N becomes or B1 greater than A1. Okay, so here we can rewrite this as not Q implies not P. Okay, these are equivalent statements, right? Either I prove P implies Q or I prove not Q implies not P. So sometimes it helps if I go in a contrapositive way. So let us try to now write this not Q implies not P statement now. I mean, we already written this, but so in terms of probability, this would mean, because everything is like kind of characterized with some probability, right? So in terms of probability, we just have to put PP here. Okay, so P LDHS greater than epsilon is S from the distributions that we take, and this is less than equal to P S over these samples, right? And then B naught less than A naught or B1 greater than A1. So if P implies Q, then if we apply probability, then it becomes less. Okay, because say P implies Q, if I have to write, then probability of P will be less than equal to probability of Q. Okay, so that's what we have done here. So okay, so this is what we are supposed to and we have or here, right? So probability of A or B, right? We can apply the union bound, right? Probability of A or probability of B is less than equal to probability of A plus probability of B. Okay, so recall union bound. Right? So this is what we are going to do. This is an event that B naught less than A naught. This is event that B1. So this is AB. So this guy is less than equal to probability that SDM and B naught less than A naught plus probability that SDM B1 greater than A1, union bound. Now we have to look into this individual terms, right? So the event B naught less than A naught happens if and only if all examples in S are not in the interval A naught A star. So B naught less than A naught exactly means that, right? Okay, that's fine, right? So B naught is less than A naught means that A naught was somewhere here, right? Yeah, I think this figure is fine, right? So if B naught was here, right? If B naught is less than A naught, then this means that the samples, right? What we have sample, right? Yeah, if all the samples basically, right? So since B naught was the max of all the samples, right, with the level 1, so it means that none of the samples were in A naught A star. That's why even after taking max, I found B naught to be even less than A naught. So none of the samples were actually in A naught A star. That's the only way B naught must be less than A naught. Okay. So the first one is the event B naught less than A naught happens if and only if all examples in S are not in the interval, are not in the interval a naught a star, a naught a star. Okay, and earlier we have written that a naught a star is the probability of finding a point x in this interval a naught a star was epsilon, right? So the interval length is such that the probability of finding a point in that interval was epsilon. We said that, right? And also between a star and a1 the probability was epsilon. So that we are going to use here. Okay, so are not in the interval a naught a star whose probability mass is defined to be epsilon, right? So whose probability mass is defined to be epsilon. Okay, so this is something we have written before. So this was length was kind of epsilon. You can think of this kind of a length, but it's about probability. So is defined to be epsilon. So then, yeah, so we will kind of characterize this now. So again, we can use this. Okay. So then we can say that S from dm b naught less than a naught is probability S samples coming from dm for all x y in S x naught in a naught a star is 1 minus epsilon to the m. Okay, so for all x, so if b naught is less than a naught, right, then what does this mean? It means that all the points x with label y, okay, yeah, so for all the points x in S, x was not in not being in a naught a star, meaning x was not in a naught and a star, and b naught being less than a naught means that for all the sample points which were outside, their probability is 1 minus epsilon, and there are m sample points. So this guy and this guy, so total sample points are m, right? So for all the, because b naught is less than a naught, so isn't this I was thinking m by 2, or because some points could be other side. Yeah, even for the other one, it's fine, right? So other half also will be 1 minus epsilon. Okay, the sample contains both the positive and negative samples. So for each of them, there are m samples, there are m data points. If b naught is less than a naught, yeah, if I'm not sure if should remain m, or I'm doing mistake here. I mean, in the book it's m, or initially sample was m, right? Not 2m maybe. Okay, whatever. Yeah, I think this is for all. Okay, so b naught less than a naught, right? A star is this one, a naught is this one, this guy is epsilon. So that's fine. Okay, so the probability that b naught less than a naught, so b naught will be somewhere here. So that means that none of the sample points were in a naught a star. Okay, that makes sense. Okay, so b naught less than a naught means that none of them showed up here. It could be here also, it's fine. Okay, but certainly they didn't show up here, because if it was here, b naught would have been that one. So these guys were also there, but these guys are also not in a naught a star. So the the zero the label samples with 0, right? These guys are obviously not in a naught a star, but b naught being less than a naught means these guys are not in a, certainly not here. Any of them, if it were here, b naught would have been there, and these guys are still not there. So all the data points are not in A naught A star. So there are m data points. So the probability of these guys being not here is 1 minus epsilon, right? So I have to do it m times, right? For each data point 1 minus epsilon, for another data point 1 minus epsilon. So the total probability of them, all of them not being in this, is product of all these probabilities, because these are independent, right? So is 1 minus epsilon to the m. We are just taking this part, okay, because this is bisymmetry. This also works in the same way. So we are just taking this part and trying to bound this. Same argument will hold here, but okay, so let us first see this part, and then okay, and this we can approximate this with a with some algebraic trick, is like epsilon e to the minus. So you can look up into this. That's less than exponential of minus epsilon m. There is a little bit of conflict here, but I'm trying to figure out why. So here it's written since we assume m less greater than log, but when did we assume this, right? So here it's written since we assume that m greater than log 2 by delta by epsilon, right? But what we assumed in the lemma is this, right? M is less than, so I'm a bit lost, like when did we assume this, right? So since we assume m greater than log 2 by delta, but there I see m less than floor of log 2 by delta by epsilon. So since we assume this, the further it says that it follows that the equation is at most delta by 2. Okay, that is fine. Like if m satisfies this, then we can solve for that is delta by 2. But what I'm wondering is, where was this, right? It seems that it went in the contrapositive that we took. It seems like the book doesn't say anywhere where it just flipped, right? So if you remember, P implies Q, right? So P implies Q was for this sample complexity, right? So the LDHS less than epsilon is when B naught if B naught is greater than A naught, P1 less than A1 for all m less than log thing, right? But if we take a negation of that, then it will become greater now. Oh yeah, the sample complexity is that, okay. So if we can ensure m to be at least this, then we are safe, right? That's what it says. So that's fine, right? If we can make the samples at least log 2 by delta by epsilon, then we are safe, right? Because at least we will take that. So with a minimum samples this, now we can like solve for this, right? Okay, so m epsilon is greater than log and so on, right? Then I can take exponential and log and all those goes away, and eventually we get that, right? So if m greater than, so m epsilon greater than log 2 by delta and exponential, then this, and then e minus, I will flip it, then the e minus m epsilon is less than delta by 2. This is what we wanted, right? So if I take a sample which is at least log 2 by delta by epsilon, then I guarantee that this probability is less than delta by 2, and this is delta by 2, and this same argument, because it's symmetric, right? So this is also delta by 2, so combine its delta less than delta. Delta is there, right? It comes in sample complexity itself. Delta is here, right? Delta is the confidence, right? Confidence of picking a sample. So this is from the pack learning, right? So I hope you got this. Okay, so this is probability, and this is less than delta by 2, and this guy is also less than delta by 2. So this is let us say further less than delta by 2 plus delta by 2, which is delta. So the probability that I will make a test error which is greater than epsilon is less than delta. So all this is coming from not q implies not p, right? What we proved eventually, right, is LDHS is less than equal to epsilon. Okay, if both B naught greater than equal to A naught and B1 less than equal to A1. So we formed a knot of that, right? And so essentially we proved this statement. So if B naught is greater than A naught, B1 is less than A1, and this will be captured by delta, right? Because that's the confidence in the sample that we saw also before. Okay, that's characterized by delta, because if B naught is not in A naught, then it tells you that it's a bad sample. Okay, so this this is less than this if you have a sample with a confidence that B naught is with a probability very high that B naught is greater than A naught and B1 is less than A1. You can do it in the other way. Then you can say with confidence 1 minus delta. Here it's greater, right? There it's less. So I can also say in the reverse way. Then it will be 1 minus delta, right? So probability of this happens is with confidence 1 minus delta. Okay, so these are equivalent statements. Here delta means probability of picking a non-representative sample, right? If you recall. So if probability of picking a non-representative sample is very small, then I'm not going to make, I mean, the probability that my error will be greater than epsilon will be very, very small, because my delta is small, meaning I don't have a non-representative sample. And the another way to say is that the probability that I make a less error is with confidence very high, because delta is small. Non-representative sample is small, then my confidence on sample is 1 minus delta, which is very high. So these are two different ways to see the same thing, right? If non-representative sample choice was very low, then also is the same way that my error making more than epsilon errors will be very low, because delta was very low, small, very small fraction was, very small probability was there for bad sample. So both ways are fine, right? So I won't be able to complete, but yeah, but just the scattering I can define a little bit and then prove in the next one. Okay, so maybe 10-15 minutes I will do, and then yeah. So or should I do it next time, because this is the next part, VC dimension, which is the actual one. If I do a little bit, then I have to repeat again. The problem is, yeah, if I do it, I won't go to the main theorem. That's the problem, because going up to main theorem will take, before that I have to spend like 1 hour just to explain VC dimension. Then I can prove a theorem. So even to explain VC dimension, I need to explain scattering with lot of examples. Then what do you want? That's all for today, or I can continue? What do you want? It's 2 hours. Okay, then let us stop. It's a valid. Let us start VC dimension as a next. Yeah. Okay, then let us stop.